Earthquakes, nature's powerful force. Understanding the violent tremors that shake our planet and the devastating waves they can create. What is an earthquake? A violent tremor in the Earth's crust that sends vibrating waves in all directions. Sudden movements that occur from disturbances within and below the Earth's surface. The science behind earthquakes. Stress builds up. Tension accumulates within the Earth's crust along fractures and fault lines over time. Critical point reached. When stress reaches a certain intensity, the crust can no longer withstand the pressure. Sudden release. Cracks or slips occur within the crust, producing shock waves that create vibrations. Primary causes of earthquakes. Tectonic plate collision. Most earthquakes result from collisions between tectonic plates, creating fractures and faults in the Earth's crust. Molten rock movement. Movement of molten rock below or within the crust creates pressure and instability. Stress release. Sudden release of stress that is slowly built up along fault lines over extended periods. Understanding earthquake anatomy. Origin and focus. The precise point deep within the Earth where an earthquake's seismic energy is first released due to rock rupture. Intensity. A measure of the observed effects of an earthquake on the Earth's surface, people and structures, typically described using scales like the modified Mercalli intensity scale. Epicenter. The geographical point on the Earth's surface located directly above the earthquake's focus. This is where the strongest shaking is typically felt. Magnitude. A quantitative measure of the total energy released by an earthquake at its source, determined from seismic wave amplitude recorded by seismographs, often using the Richter, or moment magnitude scale. Measuring earthquakes. Seismograph. Specialized instrument that records vibrations produced by earthquakes, providing crucial data for analysis. Richter scale. Measures the magnitude of earthquake shock, quantifying the total amount of energy released during the event. The birth of tsunamis. When earthquakes occur on the seafloor, they displace large volumes of water, initiating one of nature's most devastating phenomena. These powerful underwater seismic events generate immense waves known as tsunamis, capable of reaching heights exceeding 10 meters. Tsunami formation process. Seafloor earthquake. Sudden movement of the ocean floor displaces massive amounts of water above. Wave generation. Displaced water creates powerful waves that travel across the ocean at high speeds. Coastal impact. Waves grow in height as they approach shallow coastal waters, creating devastating impacts. Devastating tsunami effects. Human impact. Massive waves invade coastal lands, drowning people and causing widespread casualties across affected regions. Livestock losses. Animals in coastal areas face severe threats from the powerful waves and flooding. Infrastructure destruction. Buildings, homes, and critical infrastructure are demolished by the immense force of tsunami waves. The Erzincan earthquake and tsunami, 1939. A devastating example of combined seismic and aquatic destruction. Seismic origins. The 1939 Erzincan earthquake, a magnitude 7.9 event, caused widespread devastation in eastern Turkey, demonstrating the immense power of tectonic forces. Tsunami generation. While often associated with ocean floors, significant seismic activity can trigger tsunamis in enclosed bodies of water, like the Black Sea, impacting coastal regions. Dual impact. The event highlighted the compounding effects of an earthquake's initial destruction, combined with subsequent tsunami waves, overwhelming emergency responses and infrastructure. Turkey, 1939. A catastrophic event. Lives lost. 50,000 people killed by the earthquake and accompanying tsunami waves on December 27, 1939. Homes destroyed. 100,000 houses completely demolished by the natural disaster, leaving countless families homeless. The power of seismic waves. Distinct wave types. Earthquake vibrations travel through the Earth in multiple wave types, each possessing unique characteristics and varying impacts on structures and the environment. Energy propagation and impact. These powerful waves effectively carry the immense energy released at an earthquake's focus, enabling the widespread propagation of destruction across significant geographical distances. Fault lines. Earth's weak points. What are fault lines? Fractures in the Earth's crust where tectonic plates meet, creating zones of weakness and instability. These areas are prone to sudden movements as stress accumulates over time along the fault boundaries. Tectonic stress release. As tectonic plates attempt to move past each other, friction causes stress to build up. When this stress exceeds the strength of the rocks, it is released in the form of an earthquake. Tectonic plate movement. The Earth's surface consists of massive plates that constantly move, creating the conditions for earthquakes. This movement generates significant geological forces. Converging plates. Two tectonic plates move towards each other, initiating intense geological interactions. Fault zone formation. The accumulated stress leads to fractures in the Earth's crust, forming fault lines, which are zones of weakness. Stress accumulation. As plates converge or slide past each other, immense pressure builds up along their boundaries. Sudden release. When the stress exceeds the strength of the rocks, energy is suddenly released, causing an earthquake rupture. Energy release and magnitude. Energy release. Total seismic energy release during an earthquake event, measured by the Richter scale. Scale increase. Each whole number increase on the Richter scale represents 10 times more energy release. Modern earthquake detection. Seismic monitoring. Global network of seismographs continuously monitor Earth movements and detect earthquake activity. Data analysis. Advanced computer systems analyze seismic data to determine earthquake location, magnitude, and intensity. Warning systems. Early warning systems alert populations to incoming seismic waves, providing precious seconds for safety measures. Global earthquake zones. Geological characteristics. Certain regions of the world experience more frequent and intense earthquake activity due to their unique geological characteristics, primarily the movement of tectonic plates. The Pacific Ring of Fire. The Ring of Fire, encircling the Pacific Ocean, is a prime example of an active zone, accounting for approximately 90% of the world's earthquakes. This area is characterized by a horseshoe-shaped string of volcanoes and seismic activity. Earthquake preparedness. Emergency supplies. Maintain emergency kits with water, food, first aid supplies, and communication devices for earthquake situations. Building safety. Ensure structures meet seismic building codes and retrofit older buildings to withstand earthquake forces. Evacuation plans. Develop and practice family emergency plans, including safe meeting points and evacuation routes. The continuing study of earthquakes. Scientists continue to advance our understanding of seismic activity through research and technology, improve prediction, advance capabilities for predicting seismic events to enhance preparedness and reduce risk. Enhanced warning systems. Strengthen tsunami warning systems to provide timely alerts and save lives. Better materials and techniques. Develop and implement superior building materials and construction techniques for seismic resilience. Understand seismic patterns. Analyze long-term seismic patterns to gain deeper insights into earthquake behavior and geological processes. Understanding Earth's power. Dynamic forces. Earthquakes are powerful reminders of the dynamic forces that continuously shape our planet's surface and interior. These forces are a natural part of Earth's ongoing geological evolution. Mitigation through knowledge. Through continued study, advanced technology, and comprehensive preparation strategies, we can enhance our ability to protect communities from the devastating impacts of these natural phenomena. Preparedness is key. Knowledge of seismic activity, combined with effective preparedness measures, constitutes our most robust defense against the unpredictable and formidable forces of nature.